So to put all this to the test, we're going to use something called a force table. Here's a force table. You can tell it's a force table. See right there? It says force table. How you like them apples? Believe it or don't, this contraption is almost identical to the one that Galileo had way back in the day. And if you're curious enough, you can fish around and get pictures of the thing. It's in a museum somewhere. Now, what a force table does is, if you look closely, you can see that it's got the degree scale throughout, so 0, 90, 180, 270 in the scale, and it has an outer scale that goes in the opposite direction, or as we say here in Maine, opposite. But we're going to use the inner scale just to keep it straight with what we've been doing on paper thus far. What I propose to do is to duplicate this system of force vectors, vectors 1, 2, and 3, plus the equilibrium vector. If everything that we've been talking about thus far is correct, if our numbers are correct, if we can duplicate that system of forces on this force table, you see this little ring right here that goes right around this post? We should be able to get it so that that ring floats without touching that post. Or in other words, we're going to float the donut. All right, so that's the goal, is to float the donut. We're going to need weights, but we have a little bit of a problem here. We're going to be using these, what are called slotted weights, or more correctly, slotted masses. Why? Because they are given in grams. If you look closely, you see that they're indicated in grams. So we have to convert grams into newtons. How do we do that? Well, that's actually pretty straightforward. It's something that we've been talking about for a while. It goes to the second most famous equation in the world that articulates the relationship between mass and force. Don't be confused. You've heard it already. Force equals mass times acceleration. There it is. So, that means that mass equals force divided by acceleration. Okay, so we want to convert that mass into force, right? We want to be able to convert force into mass. All right, so the first thing we'll do is we need to know that mass, which is kilograms, is going to equal force, which is newtons, divided by A. Now, what is A? Something we haven't really talked about much. It's acceleration. In this case, we're referring to the acceleration of Earth's gravity. We haven't gotten into that yet, but I'll give you the value of it. The value of A in terms of Earth's gravity is 9.8 meters per second squared. So that would be our conversion factor. So kilograms is going to equal newtons over 9.8, and newtons is going to equal kilograms times 9.8. Force equals mass times acceleration. Mass equals force divided by acceleration. That's how we're going to do it. So first, we need to convert our newtons into kilograms and then into grams. So I want mass, so I'm going to take my newtons, 3.1, divided by 9.8, and I get 0.613 kilograms, 316 rather, 0.316 kilograms, which equals 316 grams. 2 newtons. 2 divided by 9.8, 0.204 kilograms, which is 204 grams. 1.6 newtons. 1.6 divided by 9.8, 0.163 kilograms. equals 163. Okay? And we can't forget this guy. 4.739 divided by 9.8, 0.484. Go. So now we have the values that we can use. So now I'm going to see if I can duplicate this system. So let's come over here and get an up close look at how this goes. The first vector, vector 1, is at 33 degrees. So I'll set that up right here to 33 degrees. And the next vector is 103 degrees using the inner scale. And vector 3 is 338 degrees, which is right there. And my equilibrium vector is 219.9 degrees, which we can be forgiven if we just round that into 220, which is right here. Now, each of these hangers are 50 grams apiece, so we have to take that into consideration. We have to include their mass. So vector 1, I want to have a grand total of 316 grams. So there's 50 grams, 100 grams, 200 grams, 300 grams, and where are my small ones here? Oh, there's some of them. Okay, 310. And interestingly, a nickel is 5 grams, so we're going to use a nickel. So that gets us to 315 grams. You know what? Close enough for science. All right, the next one, we need 204 grams. So there's 50 grams plus 50 is 100, 200. And we use a penny, which is 2.5 grams. So we use 2 pennies. That'll get us up to 205 grams. Here we go. Vector 3, 163 grams, so there's 50, 150. Let me find, see if I can find one. There we go. There's some more right there. $160. Add a penny, that'll get us 162.5 grams. That's close enough. Now here's the big guy, 484 grams. So 50, 150, 250, 350, 450. Put a 20 in there. 20. Yes, that's a 20. 470. 475. 480. 485. Now, there is some friction on these pulleys, but if you play with it just a little bit, look at that. Get up close and show. There it is. That's called floating the donut right there. What do you know? Physics works. You can see. Perfect. So, this is what physics in particular, science in general, is all about. is having an overarching idea, an overarching theory of how things work, and repeatedly putting it to the test and getting the same results over and over and over again. I want to show you one other way of evaluating vectors that also takes a slightly different approach in terms of the scientific method, but that comes next.